Hi everybody, welcome to the class Optical Communication Unit 2 Transmission Characteristics of Optical Fiber. In previous session we have seen the short introduction about dispersion and what are the major effects of dispersion. And today's class in detail we are going to see about intramodal dispersion and the types of intramodal dispersion. So intramodal dispersion, also known as chromatic dispersion, or you can name it as a group velocity dispersion. This mainly occurs within a particular mode. Okay. There are two types of dispersion. One is material dispersion, other one is waveguide dispersion. Material dispersion is mainly depends on the refractive index of your fiber, and your waveguide dispersion is mainly due to the guidance effects within a fiber structure. So this dispersion will leads to overlapping among the adjacent bits that causes ISI, okay, that restricts the rate at which the data can be transient over the fiber. Now we will see the types of dispersion. The first type is material dispersion. Material dispersion arises from the dependence of the refractive index of the fiber material on the wavelength of light. In order to estimate the effect of material dispersion on pulse broadening, consider a plane wave propagating through a homogeneous dielectric medium of refractive index n1. The propagation constant beta can be expressed as, please wait, let me take a pen. So, a propagation constant beta can be expressed as beta is equal to 2 pi by lambda n1 of lambda. So, n1 is the refractive index of your propagation medium. Okay. So, we all know the basic definition for your propagation constant. It is 2 pi by lambda. Since we are discussing for an optical fiber, your beta is expressed as 2 pi by lambda into n1. Okay, at a particular wavelength lambda. So, therefore, if I'm differentiating this beta with respect to lambda, so dB beta by d lambda is equal to 2 pi, which is nothing but n1 divided by lambda square plus 1 by lambda into dn1 by d lambda. Okay, if I simplify it, you will get minus 2 pi by lambda square n1 minus lambda dn1 by d lambda. I am going to consider the value within a bracket as capital N1. This capital N1 is nothing but group index, that because the group velocity of the wave can be expressed in terms of this parameter. Okay, so where your group index N1 is equal to N1 minus lambda into dN1 by d lambda. This is equation 3. So first equation, that is nothing but your propagation constant, your beta value, and a second expression you are getting by differentiating your beta with respect to lambda, and a third expression is your group index parameter, that is your capital N1. Now let us see what is that group velocity. How to obtain this group velocity? The group velocity can be obtained as Vg is equal to d beta by d omega the whole inverse. So I can rewrite the equation as d beta by d lambda into d lambda by d beta. Just I am multiplying, dividing by d lambda. Okay. What is this? Omega is nothing but angular velocity, which is equal to 2 pi into c by lambda. Sorry, angular frequency. Omega is equal to 2 pi into c by lambda. When I am differentiating with respect to lambda, you will get d omega by d lambda is equal to minus 2 pi c divided by lambda square. This is the equation 6. Now I am going to substitute the equation 6 in equation 4. You will get a group velocity Vg is equal to minus 2 pi c by lambda square into d beta by d lambda the whole inverse. Okay. So using this equation 2, okay, using this equation dB by d lambda and using this equation 7 Vg, we can express the group velocity as Vg is equal to c by n1. The group delay in the optical fiber over a length L arising from the group velocity of the spectral components can be expressed as tau g is equal to L by Vg. Okay, so here you are going to express your group velocity for a spectral components with respect to a group delay and a length L. Of course, we all know the basic formula, velocity is equal to distance by time. With that formula, we are going to write time is equal to distance by velocity. So therefore, tau g is equal to L by Vg. L is your length, or you can say length of your fiber. Vg is your group velocity. In previous equation, we have discussed what is that Vg. Okay. So it is L by C into N1. Okay, what is your Vg? Vg is C by N1. So here substitute, you will get L by C into N1. Okay, we know the parameter L1 is nothing but group index, which is nothing but N1 minus lambda dN1 by d lambda. This I am getting from the equation 3. Okay. So for material dispersion, the group delay is denoted as tau mat, and therefore the tau mat is equal to L by C into N1 minus lambda dN1 by d lambda. So this is your tau mat, that is nothing but your group delay. Okay, your material dispersion is mainly occurred due to group delay. Okay, so tau mat is equal to tau g. Okay, consider that the source used for launching power into optical fiber operates at a wavelength lambda and has a RMS spectral width of sigma lambda. So the RMS pulse broadening due to material dispersion sigma lambda can be obtained from Taylor series expansions of the equation 10, obtaining the operating wavelength as lambda. So when I'm expanding this equation 10, okay, by using Taylor series, you will get the sigma mat is equal to d tau mat divided by d lambda into sigma lambda plus 2 into d square tau mat divided by d lambda square into sigma lambda plus etc. So this you can continue with the help of the Taylor series expansion. Now neglecting the effect of higher order derivatives, which are generally small as compared to the first order derivative, particularly for the sources used in the near infrared region, we may approximate the material dispersion as, okay, sigma mat is approximately equal to d tau mat divided by d lambda into sigma lambda. So here I am considering only the first order derivative and neglecting all the higher order derivatives. Okay. So using equation 10, we may derive the dependence of group delay due to material dispersion on wavelength as d tau mat by d lambda. So here I have what is tau mat, that is the equation 10. I am going to differentiate that tau mat with respect to d lambda. Okay. So if you differentiate, you will get the equation 30. Okay. I am going to substitute this equation 30. Okay. In equation 12. So when I am substituting, you will get sigma mat is equal to L sigma lambda divided by C modulus of lambda into d square n1 divided by d lambda square. Here L represents your length and C is your velocity. Sigma lambda is your spectral width, and your source is operating at the wavelength lambda. Okay. So from this equation 14, you can clearly understand that your material dispersion is purely depends on the refractive index variation. Okay, that is d square n1 divided by d lambda. The material dispersion on optical fiber is often designated by a dispersion d parameter defined for material dispersion as d mat is equal to 1 by L d tau mat divided by d lambda. Okay. So if you substitute d tau mat divided by d lambda, you will get equation 15. So this equation 15 is your dispersion parameter, that is your d mat. So your d mat is a function of wavelength. So when I want to reduce the dispersion, I have to increase the wavelength. So that is a relation between the d mat and your wavelength. So the variation of the material dispersion parameter d mat with the wavelength of a light is shown in this figure. So when I am increasing the wavelength, when your source is operated at a wavelength 1.3, okay, your dispersion will be very less. In other words, we can say when your light source is operated at 1300 nanometer, your dispersion is 0. Okay, so that wavelength is commonly chosen for lower dispersion. Till now we have seen what is material dispersion, how this material dispersion occurs, how to derive the material dispersion parameter dmat, okay, with the help of group delay and group velocity equation. So in next class we are going to see about waveguide dispersion. Thank you.